This video will cover linear, time-invariant systems. So first, let me restate the big picture. In this course, we want to understand how to model and characterize the output signals of physical systems in response to various input signals. Let's take a look at this system, which is a tuned liquid column damper system. This system consists of a mass, and in the bottom of this video, we could see that it has a moving platform. The structures holding up the mass can be modeled as springs, and the U-shaped piece containing liquid can be modeled as a damper. This system has an input at the moving platform, and because of this input, the system has an output. So let's draw this system using mechanical elements. Here we see a drawing of the system. We can see the mass, which is connected to a spring and a damper, and the spring and damper are connected to a movable platform. The input, y of t, is shown above the movable platform, and the output, x of t, is shown above the mass. From this drawing, we can sketch a free body diagram. And if we sketch the free body diagram at the mass, we see that the output x is in the positive direction and it's going to the right, and the restoring forces of the spring and the damper, which are given by Hooke's law and the constitutive equation for a damper respectively, are shown going to the left. Now, applying Newton's second law, we could obtain the equation of motion for the system, and we could put it in canonical form, and that is shown here on the bottom. Now let's discuss the governing equation for this system. We say that this governing equation is linear, and it's linear because x and its derivatives are raised to the first power only. It is also linear because x and its derivatives are not multiplied by other functions of x. We could also say this governing equation is time invariant, and this is because its coefficients, such as b over m and k over m, are constants. They do not change with time. Therefore, the governing equation of this mass damper spring system is a linear time invariant differential equation, or an LTI differential equation. Now let's take a look at a different system. Here we see a vertical mechanical system. Here we see a mass, which is connected to a fixed reference position at x sub 0 by a black spring and a red damper. The mass is also connected to a green spring with spring constant k sub 2, which is then connected to a movable platform. In this case, we will assume static equilibrium. This means that gravity is already taken into account. Now this system has a displacement input, y of t, at the movable platform, and the system has an output, x sub 1 of t. Now that we've sketched this mechanical system, we can now draw the free body diagram. The free body diagram shows that the positive direction is up, and the restoring forces of the springs and the damper are acting in the opposite direction. The restoring forces of the springs are given by the spring constant times x near minus x far, and the constitutive equation of the damper is given by the viscous friction coefficient times x dot sub 1 minus x dot sub 0. Because the reference position x sub 0 is fixed, x sub 0 and x dot sub 0 can be neglected. From this free body diagram, we could apply Newton's second law and obtain the governing equation, and by dividing through by mass, we get the governing equation in canonical form. Let's take a closer look at the governing equation for this vertical system. This governing equation is linear. Again, it's linear because x sub 1 and its derivatives are raised to the first power only. It's also linear because x sub 1 and its derivatives are not multiplied by other functions of x sub 1. This governing equation is also time invariant because the coefficients, such as b over m and 1 over m times k sub 1 plus k sub 2, are constants. They don't change with time. Therefore, the governing equation of this vertical system is an LTI differential equation. Now, all of the mechanical and, as you will see in future videos, electrical elements used in this course are linear and time invariant, and therefore the systems that we will be analyzing produce linear time invariant differential equations. Now let's talk about a general case. Here you see an nth order ordinary differential equation. This equation has coefficients that are constant and do not vary with time. Furthermore, x and its derivatives are raised to the first power only, and x and its derivatives are not multiplied by other functions of x. Therefore, the above nth order ordinary differential equation is a linear time invariant differential equation. Now let's take a look at the right side. If f is equal to 0, then this equation is said to be homogeneous. The output, x, is therefore called the free response, and the output is caused by the initial conditions imparted on the system only and not by any inputs. Now, if the right side, if f does not equal 0, then the equation is said to be non-homogeneous. X is called the forced response, and x depends on the initial conditions imparted on the system and any external inputs, such as a force input or a displacement input. So the equations that we have discussed thus far are all linear time invariant differential equations. What are examples of non-LTI differential equations? Let's take a look at this equation. This is a linear time varying differential equation. The reason why it's a linear equation are because x and its derivatives are raised to the first power only, and x and its derivatives are not multiplied by other functions of x. However, this is a time-varying differential equation because the coefficient 1 minus cosine 2t varies with time. Let's take a look at another example. Here we see another equation, and this is a nonlinear differential equation. This is nonlinear because x is raised to the second power. We see x squared in the equation. Furthermore, the first derivative of x with respect to time is multiplied by x squared minus 1. In this course, we will deal with systems that can be represented by linear time invariant ordinary differential equations. And we say that a system is an LTI system when scaling and superposition hold. When we say scaling holds, we say that if the input to a system is scaled by a certain amount, then the output of the system will also be scaled by that same amount. So if the input to the system is doubled, then the output of the system will also be doubled. What is superposition? Well, the response of a system to 3 inputs is simply the sum of the responses to each input considered individually. So when we say superposition holds, we say that if a system has, say, n number of inputs, then the response of the system is simply the sum of the responses to each of those n number of inputs considered individually. So a system is also time invariant when its parameters remain constant during operation. This system behaves today as it did yesterday and will behave the same way tomorrow, next week, a year from now, and so on and so forth. That's what makes a system time invariant. Now I will summarize the key points of this video. In this course, we will deal with systems that can be represented by linear time invariant ordinary differential equations. What are the characteristics of an LTI ordinary differential equation? So if you're given an ordinary differential equations, take a look at x and its derivatives. If x and its derivatives are raised to the first power only and are not multiplied by other functions of x, you have a linear ordinary differential equation. Then you take a look at the coefficients. If the coefficients of all terms are constant, do not vary with time, then you have a time invariant ordinary differential equation. If your differential equation exhibits these characteristics, then it is an LTI ordinary differential equation. Now it's time for a quiz. Assuming that all of the coefficients in the equations shown below are constants, which of the following equations is not a LTI equation? The correct answer is D. This is because x is raised to the third power, which makes the equation nonlinear. In A, B, and C, we see that x and its derivatives are raised to the first power only, and x and its derivatives are not multiplied by other functions of x. Coefficients are assumed to be constants, which makes A, B, and C LTI equations. The input in option C is a sinusoid, and the equation is a second-order equation written in canonical form, and therefore it is also an LTI equation. D is not a LTI equation. This is the last of our videos on mechanical systems. At this point, you should know how to draw a lumped element model of a system and its corresponding free body diagram, and then obtain its governing equation in canonical form. The rest of the videos in this week's video set will provide you with an introduction to signals. The videos will cover topics such as taxonomy of signals, continuous time signals, and signal transformations.